Alright, so in the DQN method, we will generate the Q values using a neural network instead of looking it up from a table. And this can be very useful because the number of potential states can be very large in a certain environment. So it will be very hard to create a table that includes all the possible combinations of every state that we can have in the environment. So the Q table method works only for very small or very simple cases. But for more complex cases where we start to have a lot of possible states for the environment, we're going to have to need a different method in order to generate the Q values and select the action. All right, so what is the input for this neural network and what is going to be the output for this neural network? The input to the neural network will be the states of the system. So for example, if the position and the velocity are the state of the system, they are going to be the input to the environment. Okay, so the input will be the position and the state and whatever describes the current state of the system. Now, the output of the neural network will be the Q value for every potential action that we can take. So for example, if we can take the following actions, which is to push right, do nothing, or push left. Let's assume that those are the three actions that we can take in this environment. So the output of the neural network will be the Q value for pushing left. Okay, assume that it's 0. The Q value for pushing or for doing nothing, let's assume it's, for example, 3. The Q value for pushing right, okay, let's assume it's 1. So it will generate the Q values for all the potential actions that we can take within the environment. And you guessed it, after generating the Q value for every potential action that we can take within the environment, we will take the action that has got the highest Q value. So we will generate the Q value and then we will get the maximum, okay, we will get the action that has got the maximum Q value. Okay, so we wish to have a neural network that generates Q values based on the state of the environment. Okay, and we hope that it will generate the highest Q value for the best action that we should take. All right, okay. All right, so again, it's the same principles that we have learned in the Q learning method using the Q table, but right now we are using a neural network instead of what? Instead of looking it up from a Q table. Because it's very hard sometimes to have a Q table that includes all the possible combination of or all the possible states that an environment can include. Okay, it can be infinitely huge. So in this case, we're going to need the Q or the DQN method. All right, so let's go right now to the Colab notebook and go throughout the tutorial. So we will learn on the system. As you can see, we're trying to train the system in order to, to balance this rod over here by pushing left, pushing right, or doing nothing, right? So here is the structure of the neural network, okay, that we will train in order to generate our Q values. Okay, it includes 3 linear layers, nothing complicated, very simple, feed-forward neural network. All right, so here is the main training loop over here. All right, let's look at the very basic structure of the training loop. We will step the environment with an action, Okay, and this will give us the observation and the reward. Okay, now, you know, in order to train a neural network, you're gonna need a batch of data. Okay, it's not gonna be enough to just have one step, okay, within the environment or something like that. So here is what we're gonna do. We will store, we will store, okay, the data within a memory. Okay, each each slot will contain the state, the action, the next state, the reward. Okay, so once we go through many steps within the environment, we will have stored a batch of data. Okay, because in order to train a neural network, you cannot just have like one step or two steps. You're gonna need a batch of steps, right? Okay, in order to successfully train the neural network, which is why we use this function, which is about storing each step outcome within a memory. Okay, so we will store the state, the action, the next state, the reward. Now, once we have enough data stored within the memory, we will optimize the model. Okay, we will train and optimize the model over here. Okay, which is to train the neural network on the batch of data that we have stored in the memory. All right, so as we know, we want to train a neural network. We need an X, which is the input, and we need a Y, right, which is the output. So, what is the update equation that we will be using in the system? You know, if we recall in the in the Q-learning using tables, okay, the previous method, if you remember, this was our update equation, right? We got the previous Q value and we add the reward, which makes sense, and we add the maximum Q value for the next state, right? Now, in the DQN method, this is going to be our update equation. Okay, it's a simpler one, just the reward and the maximum Q value for the next state. Just, okay, it's a simple equation, nothing else. So we are going to be using this equation in order to find the Y on which we will be training the network. Okay, and this is reasonable, right? Okay, because the higher the reward, the higher the Q value that we want for this action, right? And also the higher the maximum Q value for the next state, the better this action is going to be, as we have explained previously. Okay, because this action will transition us into a strong position where we will have a high Q value for our next action. It's like when you select a good product, then you can create a very successful ad campaign. But if you pick a bad product in the first step, no matter what you do in the ad campaign, you're not probably going to succeed. Okay, so if the maximum Q value for the next state action is high, then we also want the Q value for the current state action to be high as well. So this is how we can make sense out of this update equation over here. All right, so let's see that in the code. Within the code, if you go to this function that's called optimize, this is the function which we will call whenever we want to update the neural network and train it using the data that we have gathered as we are stepping through the environment and trying all sorts of different actions. So in the beginning, we say that if the memory doesn't include enough information, if the length of the memory is less than the batch size, then just don't train, just return, don't train anything, because we don't have enough data to feed into the neural network. Okay, so first we make sure that we have done enough steps within the environment that we have in order to train the neural network. So the network we are training is called the policy network. Okay, so right now, in order to train this network, we are going to need to define the loss function. So in order to train the network, we're going to need the output of the network. So we will input the state into this network and we will get the state action values. Okay. Now this is what the network is generating, right? This is what the network is generating. And we want it to be as close as possible to the training data. But how do we get the training data? From the update equation that we have just talked about. So this is the expected state action values that we have just talked about, which is the new state values times gamma plus the reward, right? Okay, just this is the equation that we have talked about over here, which is the reward plus the okay, the Q target. Okay, so we have now, so this is our X over here, and this is our Y over here. Okay, so since we have the X, which is the batch state, and we have the Y over here, we can train our neural network by feeding it into the loss criteria function. This is the output of the actual output of the neural network, and this is the target which we are trying to train upon. And the difference between them is going to represent the loss. And based on this, we train our neural network. All right, let's do some training. Let's see if we have GPU here. Okay, let's do some training in order to show you what's going on here. Okay, let's run this. Okay, and let's run this. Let's run this. And now we will also apply the SVD to the first layer of the neural network in order to smooth out the training process. Okay, this is our optimized function. And this is training with the SVD over here. And right now it is training. As we can see, the reward is going up, or the duration, which is how long we can sustain the bar, up. It's going up, which says that we are progressing nicely. So right now we have reached this duration over here. Okay, it's becoming clear right now that okay, we're still here training. Okay, we're still going down. All right. All right. So right now the duration is at 500, which is what we want, and it looks like the system has actually achieved the target, and right now it's succeeding consistently. So what's going on right now is that the system is actually succeeding at sustaining the bar for for long enough time, which is kind of like 500 seconds or whatever the the target. and right now it's stable over here. So the system has actually achieved the target. So I'm going to stop the training over here. All right. So whenever we make one step into the environment, how do we select the action? Just simply by using the model that we are training, which is called the PolicyNet, and injecting the current state into it, and generating the Q values, and getting the maximum or the action that has got the highest value. Okay, so this is how we step through the environment. We can see this in a function called select action. Okay, so simply we will we will generate the Q values for all the possible actions based on the current state, and we will find the action that has got the highest Q value, and this is going to be the action that we will perform in the environment. So this is how we step or make one step forward in the environment. All right. One last thing before we wrap up this topic is that we are going to be using two models in the training process. We will be using the first model, which is the policy network, okay, and another model, which is called the target network. Now, whenever we are predicting the Q values, okay, for each state, or choosing what action to take, we will be using the policy network. Okay. Whenever we are computing the maximum Q value for the next state, we will be using this other model over here, which is the target network. What happened is that they have found that when they used the same model in order to choose the action and also predict the Q values for the next state, that has led to an instability in the training process. Okay? So, so they have found that using two models, one for the prediction of the maximum Q values for the next state, and one for selecting the action and predicting the Q value of the current state, has led to stability in the training process. So what we do is that we train the policy network, okay, during our iterations, and then after each certain number of steps, we copy those weights into the target network. So one way is that we don't update the target network every single step. We update the policy network, and every certain number of steps, we copy those weights into the target network. Okay, so this is one way of doing it. Another way of doing it, which is used in this code, is to soft update the the target network using this formula over here. So instead of updating the target network directly, just like we update the policy network, we soft update it according to this formula. This is also another way that will lead to stable training. All right, so let's see that in the code. All right, here is our next state values, the Qs that come of the next state for which we find the max. We are using the target network. Okay, so we are using the target network model. Whenever we want to predict the Q values for the current state, we are using the policy network. Whenever we want to select the action, we are also using the policy network. Okay. So as we can see here, we are using two models because if we use only one model and use that specific model every time we want to find the Q values of the next state, okay, that will lead to an unstable training process. Okay. So the solution for this is not to update the target model every single time, to update it every few steps, okay, or every certain number of steps, okay, or to use the soft update method we have talked about. You know, in order to make things easier, assume that you're trying to learn from someone, okay? So let's assume that you are looking at this guy over here and you are trying to learn from him, okay? So assume that this guy is changing every single time, okay? So you will be puzzled, right? Because every time you are trying to learn something from him, he's changing his behavior on a consistent basis. So you will be confused. So you will say, you know what? You cannot just keep changing every single time. Okay. So if we make this guy constant for a while, at least until I learn something over here. Okay. So I would start, at least I would have learned something. Then you can change and then stay stable for a while until I learn something. But if you are trying, if this guy from which I'm learning is changing all the time, every single step, changing into something else and something else, then I'm not going to be able to learn from him because he's changing all the time. There's no consistency in his actions. So the solution for this is to, make this guy constant for a few steps until I learn something from him. And then I can allow him to change. And then I learn something from him. Okay. And so on and so forth. So this is what we're actually doing. Okay. Whenever we make the target model constant for a number of steps, or we at least soft update it, we make it constant for a while until the policy model is able to learn something. Okay. But if the target model is changing all the time, the policy model will be confused because what it's trying to learn from is changing all the time. Okay. And if you want to gain more understanding of this, you can go ahead and try and use only one model and watch the learning process or the training process and see what happens. This will also give you better understanding.